We'll now discuss some proof why A times the eigenvectors contained in P matrix will produce diagonalization. Alright, first let's assume that P is invertible, implying that P minus 1 exists. And what we'll have is that we'll have AP times P minus 1 is equals to a matrix B, let's say. And when we have P on the left hand side, to pre-multiply both, we'll have AP equals to PB. Now, if P contains eigenvectors, for example, we have called it as V1, V2, and they are distinct and independent eigenvectors, then what we will get, instead of the B matrix, any B matrix, we will get PD, where D is a diagonal matrix of eigenvalues. So this is lambda 1, lambda 2, and lambda n. Why is this so? Well, we begin with AP, and P contains V1 to Vn, where they are eigenvectors of A, and there are n independent of them, and therefore we call it a basis, because there are enough eigenvectors to form a basis. To form a basis for Rn, we need n of them, n independent vectors. Right, so we will multiply A multiplied by P. We can add A on V1 individually, and this is AV1, this is AV2, and AVN. Remember that for eigenvectors, A times x equals to lambda times x, only when x is an eigenvector. So V1, V2 are all eigenvectors, so we have AV1, therefore it must be equals to lambda 1 times V1. Now lambda 1 times V1, this guy is a constant, is a scalar, and this guy is a vector of Rn. We can of course put it as here, if this is V1, we can put it as lambda 1, a constant, multiplied by V1, or we can put V1 multiplied by a constant. It's the same. Okay? Or individual entries of it will be lambda 1 V11, lambda 1 V12, and so on. Okay? Or should I put it? Well, it will be just simply the elements of V1, and these are until the nth element of V1. What about AV2? Well, AV2 again is lambda 2 V2, or V2 times lambda 2. Again, lambda 2 is the eigenvalue, the second eigenvalue corresponding to the second eigenvector. Now, what it means is that if we, so I'll just put it this way. Now, when you want to write it as columns, and you want to relate it to P and D matrix, it is simply the columns of P, which are the eigenvector, post multiply, right hand side, multiply by D, because do it by yourself. Columns of P here will be scaled by the diagonal elements of D to get this matrix over here. Okay, so what we are saying is that a column vector V1, V2 post multiply by D11, D22, all the rest are 0, will be equals to, you look at this post multiplication, the first column of P will be affected only by D11. So this D11 multiplied by V1. The second column of P, which is V2, will only be affected by D22. So it's D22, V2, and so on and so forth until the last column. So that is why we are now saying that this guy, P times D, is equals to this representation. This reveals that if P is the eigenvectors arranged as column, then similarity transform of A will generate a matrix D that is a diagonal matrix, and the entries are simply the eigenvalues. So this completes the proof.